deep dive. Today we're getting into person re-identification, or re-ID as it's usually called.
Well, that's right.
Basically, figuring out if the person seen on this camera is the same one seen on another camera down the street.
Exactly. And it sounds simple, but it's surprisingly tricky. People look different depending on the angle, the lighting, what they're wearing.
Right. Lots of variation. Now, deep neural networks are the main tool here, learning features to, well, identify people.
Yes, they learn these complex representations from image data.
And a common technique inside these networks is self-attention. But the sources we're looking at today, a research paper mainly, plus our notes suggest maybe standard self-attention isn't quite cutting it.
Well, it might not always be focusing on the most critical visual information for actually telling people apart.
Okay, so that's our mission for this deep dive. Understanding this new approach, DCS-Attention, why it's different, more innovative, and why it seems to work better, especially looking at the academic contributions.
Sounds good.
So let's start there. What's the deal with traditional self-attention? Why isn't it always hitting the mark for re-ID?
Well, the standard way self-attention works is that it considers all the available feature channels when it's calculating these attention weights, figuring out what parts of the image are important.
All of them, equally.
Pretty much, yeah. When calculating the weights, all channels get a say. Think about try to find a friend in a crowd. You don't stare equally hard at every single brig in the wall behind them, right?
No, of course not. You look for their face, maybe their coat. Distinctive things.
Exactly. But traditional self-attention can be a bit like giving equal importance to the brooks and the coat, potentially washing out the really useful identity-specific signals.
Okay, that makes sense. Like highlighting every single word in a text, you lose the emphasis. So what's the big idea with this DCS-Attention then? How does it fix that?
The core innovation is this idea of dynamic selection. DCS-Attention, that stands for Differentiable Channel Selection Attention. It doesn't use all the channels.
Ah.
Instead, it actually learns to select and focus on only the most informative channels specifically for the task of telling people apart.
So it's way more targeted. It's not just about where the network looks in the image, but also what kind of information it's actually paying attention to at a feature level.
Precisely. Our notes call it task-oriented channel selection for that reason. It learns which visual patterns, which feature channels are best at capturing someone's unique identity.
And that's distinct from, say, features related to just general personness or background clutter.
Right. It's like your brain filtering out the background noise, the buildings, the cars, and really zooming in on maybe the specific pattern on your friend's scarf or their unique way of walking. The paper actually has figure 2, that shows this visually.
Okay, figure 2. We'll link that in the description.
It shows how DCS-Attention uses a much sparser set of channels compared to the standard approach. It's this learned selectivity that's key for the re-ID task.
Okay, now this is where it gets academically interesting, I think. How does it do that selection? It's not like someone is manually picking channels, right?
No, definitely not. It's learned. The mechanism behind it is called Differentiable Channel Selection, or DCS. The paper explains it uses what they call a binary decision mask.
Binary, so like on or off, this channel is in, this one is out.
Essentially, yes. For each channel, the mask makes a decision, use it for the attention calculation, or ignore it.
But wait, binary decisions, on-off choices, those are usually a nightmare for training neural networks, aren't they? Gradient descent like smooth changes, not hard switches.
You've hit on the exact challenge. And that's where another piece of innovation comes in, the Gumbel softmax trick.
Gumbel softmax, okay.
Yeah, it's a technique that provides a way to make this discrete, binary-like selection process effectively differentiable. Think of it as a clever workaround.
So it lets the network learn these on-off decisions using standard training methods. How does that work?
Kind of. During the forward pass, when the network is making a prediction, Gumbel softmax helps make a pretty firm, almost binary choice about the channels. But crucially, during the backward pass, when the network learns from errors,
during backpropagation.
Exactly. It uses a continuous, smooth approximation of that choice. This lets the gradients flow back properly, telling the network which channel selections were, better or worse for the final re-ID task.
So it learns which channels to probably turn on.
Yeah, it learns the probabilities, and the Gumbel trick allows sampling from those probabilities in a way that looks discrete but behaves smoothly for learning. This whole dynamic learn selection via Gumbel softmax is really a central part of the novelty here.
This focus on selecting only the necessary information. It sounds efficient. It actually reminds me of the information bottleneck principle. Our sources mention that too.
Absolutely. That's a key connection the paper makes. The information bottleneck, or IB principle, is this idea that for any given task, the ideal representation of your data should squeeze out all the irrelevant stuff.
Like noise.
Exactly. Noise, redundant details, anything that doesn't help with the specific task at hand. For re-ID, that means holding on to identity features and ditching variations from, say, lighting changes or different viewpoints.
So DCS-Attention is like a practical implementation of the IB principle for attention mechanisms in re-ID. It's actively trying to bottleneck the information at the channel level.
That's a great way to put it. The paper argues that while people have used attention and re-ID a lot, they haven't really focused on applying this IB idea to select the input channels for the attention mechanism itself.
Interesting.
And they take it a step further. They actually incorporate an information bottleneck loss, IB loss, into the training. Well, technically, they use a variational upper bound of it called IBB, which is easier to compute.
Okay, so there's a specific loss function pushing the network towards this information efficiency.
Yes, equation 4 in the paper shows how they add this IBB term to the main re-ID loss. Minimizing this combined loss explicitly encourages the network to learn representations that are both good for identifying people and informationally compact, just like the IB principle suggests. That loss formulation is another innovative contribution.
Okay, so we have this smart channel selection mechanism, DCS-Attention, guided by the information bottleneck principle. How flexible is it? Can you just plug it into any standard re-ID network?
That's one of its strengths, actually. The paper shown it's quite versatile. They demonstrate plugging it into several existing popular network backbones. They call this DCS-FB for feature backbone.
So you can enhance networks people are already using.
Exactly. But they also explore another angle, using it within neural architecture search, or NAS.
Where the algorithm designs the network structure itself.
Right, they call this DCS-DNAS. Here, the system learns the best network architecture and the best configuration for the DCS-Attention module at the same time, jointly optimizing both.
Wow, okay, that sounds really powerful from a research angle, finding the structure and the attention mechanism together. Does the paper show results for both approaches?
It does. Table 1 has results for DCS-FB, showing it boosts performance across a range of backbones, OSNet, MobileNet v2, ResNet 50, even transformers like Transraid. Pretty consistent gains.
So it seems generally applicable. What about the DCS-DNAS, the joint search?
Table 2 focuses on that. It shows that DCS-DNAs can find models, like ones based on FB and EV2, that achieve really strong results, sometimes even state-of-the-art. Often, while being computationally quite efficient, they look at FLOPs.
Lower FLOPs meaning faster inference?
Generally, yes. And importantly, the models found by DCS-DS, especially when trained with that information bottleneck loss we talked about, tend to outperform models found by standard DNNs without DCS-Attention.
So the joint approach really pays off. The paper also uses GradCam visualizations, right? What do those show us?
Right. GradCam helps us see where the network is looking. It creates these heat maps on the input image, highlighting the regions most influential for the network's decision.
So for re-ID, you'd hope it highlights the person, specifically the useful parts.
Exactly. And figures 1, 2, and 3 in the paper compare the heat maps from standard models versus models with DCS-Attention. The difference is often quite striking.
How so?
The DCS-Attention models tend to produce heat maps that are much more focused on the actual person's body, the torso, limbs, clothing features, whereas the standard self-attention models sometimes have more diffuse attention or might even focus on irrelevant background stuff.
So it visually confirms the network is focusing better.
Yes, it gives you strong visual intuition that DCS-Attention is really guiding the network to look at the right places and using the right kinds of features from those places.
Okay, the visuals are convincing. But is there harder evidence, like quantitative proof, that the features learned by these DCS-Attention models are genuinely better for telling people apart?
Yes, they provide that too, using a couple of techniques. One is TSNE visualization.
TSNE, that's the one that tries to plot high-dimensional data in 2D, right, to see clusters.
That's the one. Figure 6 shows TSNE plots for features learned by a Transraid model with and without DCS-FB. With DCS-Attention, you see much tighter clusters for images of the same person and clearer separation between the clusters of different people.
So a better grouping of the same identity, better separation between different identities, that definitely sounds more discriminative.
It indicates a more discriminative feature space, yes. And they back this up numerically with the Fisher score.
Fisher score, what does that measure?
It's a statistical measure. Basically, it quantifies how well classes are separated by looking at the ratio of between class variance to within class variance. Higher score means better separation.
And the DCS models got higher scores.
Significantly higher, yes. They report the Fisher score for DCS-FB Transraid is much better than the baseline Transraid. It's solid numerical evidence that the learned features are more discriminative, better suited for the re-ID task.
Okay, improved accuracy, better focus, more discriminative features. Sounds great, but what's the catch? Does adding DCS attention make training take like twice as long? What's the efficiency cost?
That's a fair question. They looked into that. Table 7 in the paper addresses training time.
And
And the increase is actually pretty modest. For instance, adding DCS-FB to transwrite only added a small percentage to the overall training time.
so you get these significant performance bumps without a massive hit on training resources.
That seems to be the case, yes. It suggests it's a practical improvement, not just theoretically interesting, but computationally too expensive.
Okay, let's try to wrap this up then. We've gone through DCS attention, this new way to do attention in-person re-ID. The big innovation is the dynamic learned selection of feature channels.
Inspired by the information bottleneck principle.
Right, inspired by IB trying to keep only the truly useful info. And it works well whether you add it to existing networks, the DCS-FB approach, or learn it jointly with the network structure itself in DCS-DNAS.
Correct.
And the evidence seems solid. Better accuracy, visualizations like GradCam show it focusing correctly, and quantitative measures like TSNE and Fisher score confirm the features are more discriminative,
And all this comes with a relatively small increase in training time.
making it quite practical. It really feels like focusing on what information the attention mechanism uses, not just where it looks, is a powerful idea.
It absolutely is. That dynamic selection, driven by the TAG and guided by principles like the information bottleneck, seems like a very promising direction for making these deep models smarter and more efficient, especially for complex vision tasks.
So, for our final thought today, building on that idea, where else could this principle of dynamically selecting the most relevant information, not just spatial locations, be applied? Beyond re-ID, what other computer vision problems, or maybe even tasks outside of vision entirely that use attention, could benefit? Could focusing the input to attention mechanisms lead to breakthroughs in efficiency or accuracy elsewhere? Something to think about. Thanks for joining us on the Deep Dive. Hey there. Want to share your thoughts on this? Well, that's certainly a thought. It's interesting how we could be thinking about really technical things like neural networks, and then something personal pops into your head.
Absolutely. And in a way, it ties into what we've been discussing, this idea of focusing on what's relevant. You being 19 is a key piece of information about you, right?
Yeah, like a key feature for a person re-identification task, that might be like noticing a very specific piece of clothing someone is wearing.
Exactly. It's a salient attribute. Just like DCS attention tries to focus on the most informative feature channels for identifying a person, our brains are constantly filtering and prioritizing information.
So while we're diving deep into how AI does it, it's fascinating to think about how we humans also process and filter information in our own way.
It really is. And your thought actually highlights the complexity of identity, something these re-ID systems are trying to grapple with.
Okay, but with that little personal reflection, let's come back to our main point. This idea of where else this dynamic selection of information could be useful.
Right. Think about something like video analysis. Instead of giving equal weight to every single frame or every single pixel, you could dynamically select the most informative parts of the video for a specific task.
Like if you're trying to identify an action, you might focus on the parts of the video where the movement is most pronounced.
Precisely. Or in natural language processing, instead of attending to every word equally, maybe you could dynamically select the most semantically important phrases before calculating the overall meaning.
So like a pre-filtering step for attention, making it even more efficient and targeted.
That's the potential. It's about not just where you're looking, but what specific aspects of what you're looking at are truly important for the task at hand.
It feels like this idea of being selective about the input to the attention mechanism could be a really powerful general principle.
I agree. It's about making the attention mechanism itself smarter, giving it the tools to focus on the signal and ignore the noise right from the start.
Something to really think about as we see more and more applications of attention mechanisms across different fields.
Definitely, it opens up a lot of possibilities for more efficient and accurate AI systems.
Well, this has been a fascinating deep dive into DCS attention and its potential. Thanks for joining us on the deep dive.
It was a pleasure.
We hope you enjoyed exploring this with us, and we look forward to our next exploration. Until then.